So let's go through a hard mode Snell's law problem and then talk about when Snell's law breaks. So this is one where it's not just plug and chug where you get to just dump something into N1 and N2 and find one of the two thetas. So there's a kitty and there's a image of a fish at least somewhere located relative to the kitten. And what we want to know is, given some paw reach, I guess, can she just reach down and grab it and then have lunch? So specifically, the kitten sees, and this kitten is really good at trigonometry, we'll see if it knows Snell's law, sees that the fish is apparently 6 centimeters in front of her. So this distance would be 6 cm. And at an apparent depth, so depth would be straight down, an apparent depth of 8 centimeters. So what that means in some sense is this is where you see the thing, but of course, what do you guys know about the light ray that came from the fish, probably a reflected light ray originally from the sun. Light ray that came from the fish probably didn't go straight from water into air, right? So it probably refracted. So this is the image of the fish, and the actual fish is somewhere else. So what might be helpful, or a good place to maybe pause and think about this, is the fish actually going to be here, or is the fish actually going to be there? So where is the fish going to be actually located, given the apparent image is here? Okay, so I presume that you paused and thought about it a lot, and maybe what I would do is, just kind of to think this through a little bit, is I've got an air-water interface, and here's a kitty eye, and the kitty eye sees this and is tracing the ray back to where she thinks the fish is. But what's going to be true as I go from water, which has an index of refraction of 1.33, to air, which has an index of refraction of 1.0003, but for us 1.3 is good enough. I don't think that 0.0003 is going to make or break the cat. Okay, so because this is going from what we'll call an optically dense to an optically light medium, when I look at N1 sine theta 1, or N air sine theta air to be specific, and then N water sine theta water, what I have is that if this is less than that, what's got to be true is this has got to be greater than that. When we derive this, when we do this in waves, because you actually need to understand how waves act in order to derive Snell's law, you'll see why it's the case. But for now, what you can do is you can have the following mnemonic. So water bends towards the normal in the slower medium. So bend towards the normal in the slower medium. And there's a Jeep mnemonic for that. So the Jeep mnemonic is this. So imagine that you're driving a Jeep and you want to go from a beautiful paved surface where you're able to drive really quickly. So low index of refraction means you move faster. So in this case, light goes about as fast in air as it does in vacuum, to something where you move more slowly. So that would be kind of like driving your Jeep from paved surface to mud. And your Jeep actually has a wheelbase, right? So as your Jeep is driving, you've got your left wheel and your right wheel, and then you make it to the surface. Which wheel gets stuck in the mud first? Aha, it's this wheel. So in fact, during this period of time, the wheel itself on the right is going to move not as far as the wheel on the left. Right? So this wheel gets stuck first and slows down. The other wheel is still on pavement. You're going to bend this way. So that's the mnemonic for bend towards the normal for the slower medium. Just think about Jeep wheels. And it would be true if it was going this way too. So in this case, the left wheel going this way hits the faster medium first and then bends in the following direction. So one way or another, we know that we bend towards the normal, math or Jeep. Okay? So what I know is that I see this light ray here. I think it's coming from there. That's what the apparent image tells me. Let me clean this up a little bit. So for us, what that means is I see a fishy here, but that light ray bent. So my brain's just tracing it all the way back in a straight line, and fishy is actually here. uh-oh. So this might be a problem. So the fishy's actually a little bit farther away than we thought it would be. So apparent fishy, actual fishy. Okay, so now this is why this is the hard mode problem, is that you guys got to use actual trigonometry and sines and cosines and tangents to figure out exactly where this thing actually is. So let me clean up my diagram a bit. I came up with some terminology, so I should, for notation, so I should keep that. So there's normal, and this is theta air, and then this is theta water. So that's our Snell's law part. What we have to do is we've got to come up with the triangles that relate the apparent image of the fish to the actual image of the fish. So the apparent image of the fish comes from just tracing this back to its original location. And what we have is a triangle that looks like 8, 6, don't kill me, but I'm going to leave off units, 8 centimeters, 6 centimeters. And this actually shares the 8 centimeter side. It's just got its own adjacent side. Right? So what we're actually looking for is this. So this depth D, which is not going to be equal to 8. So trig time. So I have this depth, I can find this angle, so let me redraw this triangle. So this triangle is a is a 6 centimeter, D centimeter right triangle, and then what I know from the SATs that I took 10 billion years ago is that these are opposite interior angles, so this is actually theta water. Okay. So now what I can do is Snell's law, great. And Snell's law will tell me that n air sine theta air equals n water sine theta water. And well, I've got these, I don't have that. I also have two equal triangles, so this angle, theta air, is actually equal to that angle, theta air, and then opposite interiors again. So I have a second triangle that will help me figure out not theta water, but theta air. So that's 6, 8, theta A. So from each one of these, I can figure out, the easiest thing to do would be to figure out tangent. So I have tangent theta W is equal to 6 over D. And here from this triangle, I have tangent of theta air is equal to 6 over 8. You could also notice that this is a 3, 4, 5 right triangle, and this is 10 centimeters. If you did, good for you. And that would immediately make me think, so the null hypothesis of the cat who doesn't know Snell's law is like, cat's like, yo, this is a 3, 4, 5 right triangle. This is 6, this is 8, this is 10. Here we go. I've got an 11.5 centimeter reach. No problem. So it turns out that might not be the case. So I can arctangent this. I'm always going to be careful with arctangents because they love to lie to you. Actually, sorry, opposite over adjacent, this is 8/6, and D over A. I heard you pointing that out, I just, wasn't listening. Okay, so OH, AH, OA. Wait, no, I don't know. Good. Just kidding, I had it right the first time. Okay, so arctangent this gives me theta A is equal to 53.1 degrees, and then theta water should be less than that because we bend towards the normal and slower medium is 26.8 degrees. Wait, this is 36. Oh, I see what I did with the funny notes. Yeah, I don't know why you would make that more complicated than it needs to be. So defining the angles this way, I have theta A and I have theta water. Right? So that's just Snell's law. So I have theta A and theta water, and now what I can do is figure out what D is, again using trigonometry. So that came from Snell's law. So now finally I can figure out d because again I know that tangent of theta water, which I figured out from Snell's law, can go back into there, is 6 over d, and so that's tangent of 26.8 degrees equals 6 over d, which tells me that d is equal to 11.9 centimeters. So even if the cat hovered directly over this fish, it turns out that's too far. It's 11.6 centimeters. And the cat dies of hunger. Just kidding, they go out for a wonderful meal at Camus. So that would be kind of a, again, hard mode Snell's law problem where you actually need to puzzle through the geometry itself. While we're here, I'll point out one extra thing that happens, is that there's this tendency because, you know, life is, a lot of life is equation hunting, especially when the equations are tough, they have to be kind of pre-digested for you, is that the tricky trick that will catch people maybe half of the time is that you just won't get the Snell's law angle relative to the normal. So somebody would, for instance, instead of telling you this, they would tell you that the complement of that is 53.1. So they would tell you instead that the cat is looking above the horizon at 53.1. So watch out for this. So always make sure it's the normal. And if you just plug that blithely into Snell's law, you would not get the right answer. So that's basically giant trick number one. Okay, so let me change this a little bit. And something really phenomenal is going to happen, and you can go through the math yourself to check mine. Because I deliberately speckle some algebra errors inside of my notes to make sure you're paying attention. So let's say, I'm not even going to bother you with the trig. I'm just going to say that suppose the fish is at an angle, actual fish is at an actual angle of 60 degrees. So this is a very clever fish. So the fish swims over here and makes an angle relative to normal. So maybe it's still at the same height of 60 degrees. So let's put it over here. I guess the normal would be about there. And relative to normal would be here. And 60 degrees is pretty big. So maybe you're thinking, you foolish fish, you're going up, right? You used to be at an angle of 20 degrees, which was farther down. Now you're raising yourself up towards the surface. Clearly you're going to get caught, right? So what actually happens when we see whether or not the fish could catch the cat could catch the fish? I'll plug this without thinking into Snell's law. So I have n air sine theta air. So we're trying to figure out theta air. Maybe we'll do some trigonometry. N water sine theta water, 1.0003. And then I have 1.33 times 60, and I get 1 times sine theta is theta, and this is 1.126. So make sure my calculator's in radians, multiply sine 60 times 1.33, and then what I do is take the arc sine of this thing, the inverse sine, and what do I get, of course? My calculator catches on fire, or it gives me some sort of error message. So what happened? We broke Snell's law. So what's going on is that, sine never gets bigger than 1, right? If you look at a sine wave, it looks like this. It oscillates back and forth in between, so that would be 0, I guess. It oscillates back and forth in between +1 and -1. So there's no value of theta, you can go from negative infinity to infinity, you're never going to have a value of theta that exceeds 1. So what happened? Well, this is where total internal reflection happens. And the nice thing about it is it just happens naturally where Snell's law breaks. So if you cannot take the arc sine of a number that's greater than 1.1, what this actually means is that total internal reflection happened. And what that means from the standpoint of the fish is what happened to these light rays. So this light ray that was coming off of the fish would not leave the water at all. It would be reflected back down. So in fact, this really clever fish, by going up and up and up, has decreased or increased the angle relative to the normal. Increased the angle relative to the normal to the point where the light that's coming off the fish just doesn't even, it's not even seen. So it's completely camouflaged. Brilliant fish. Okay, so just sketching out some ideas about total internal reflection. And what I'll do at the end of all of these chapters is kind of have a roundup and show off like cool YouTube videos and demos that we wouldn't have, that we would have shown off in class, like in an actual physical classroom environment. So here's a theta, and this is theta incident. So this only works when you're going from n1, so actually a better thing to do would be call this theta 1. If theta 1 is bigger than, n1 is greater than n2, which is to say we're going from an optically slow to an optically fast medium, so going from slow to fast. Then the possibility exists that n1 sine theta 1 can actually be greater than 1, right? Or, just sine theta 1 can, that's an awkward way of writing it. So let me just start with Snell's law, because then we derive it on the way. So we're trying to refract, and if we're trying to refract, basically what we're trying to do is solve for theta 2. So the first thing we do is that sine theta 1 can never be greater than 1. If we're at a really big angle, it might be close. But because n1 is greater than n2, it might be the case that this quantity is greater than 1. So if this is greater than 1, there is no such solution for theta 2. So this being greater than 1 is the condition for total internal reflection. And what you usually do is you define a thing called the critical angle. So the critical angle for an interface, the interface has to be from A to B, is defined as this. So if you actually look at the biggest angle that you can possibly make before you go from refraction to total internal reflection, and this is one of those things that I probably wouldn't give you on a quiz, because the point is to understand where it comes from. Because there's no, the derivation of the critical angle is not any harder than just using Snell's law once. So let's say I'm going from n1, and n1 is really optically dense, so to something that's optically lighter, and there's my normal. So I've got a light ray coming in, and it's coming in at some big angle. So theta c would be where this thing actually comes out at 90 degrees. So in some sense, it's where total internal reflection happens is where, sine of this is 1. We can't get bigger than 1. So in some sense, the proof of, or the derivation of the critical angle is where n1 over n2, exactly what we have there, sine of theta c is equal to 1. Right. Actually, I'll do that in 2 steps. Sine theta 2, but then that's sine of 90, which is equal to 1. I don't know, so it's a proof. So it's like you're trying to solve for the refractive angle, but if it's bigger than 90, you've basically broken Snell's law. And if you want this, I don't think it's particularly helpful because this is enough information. You could call the critical angle the arc sine of n2 over n1. And this is only when n1 is greater than n2. Because if n2 is greater than n1, that doesn't have a solution. Okay. So let me just really quickly give you guys a problem with this. And part of the reason why gemstones like diamonds are so pretty is because they have a teeny tiny critical angle. So as light's trying to leave a diamond that has an index of refraction of 2.42 or something like that, it's pretty difficult because there's not a lot of angles before it gets to the critical angle. You don't have a lot of room. And they're cut in such a way that you're basically trying to generate total internal reflection, which is why they seem to sparkle. So. So let's find the critical angle for the air-water boundary, which is essentially the question of what calculation did this sneaky fish do before it figured out how high it would have to float up in the water column to be invisible. So this is the way that I would do things, is like not remembering any formulas, just figure out what that means. So here I have water, air, and the only way I'm going to get a critical angle or total internal reflection is if I'm leaving water and entering air, right? If I'm leaving air and entering water, it's going from fast to slow. So the angle is always going to be bent towards the water, and it's always going to be bent towards normal. So this would only happen if we go from water to air. So that's theta c, and theta c happens right as we're coming out at 90 degrees. Okay. And then I have and air sine theta air generically for Snell's law. And then n air is 1.0003, whatever we'll call it 1. Okay, now what we want is the critical angle. So that's air. What is the critical angle for air? That would be 90 degrees. And water is 1.33. And that's the thing we don't know. So we don't know theta c. And then math happens, that's 1 times 1, oh man, I love this math, equals sine theta c. And then theta c itself is the inverse sine of 1 over 1.33. And that's like 48 degrees or something, 48.75. Okay. So what the fishy did is pulled out his waterproof pocket calculator and said, as long as I'm above an angle of 48 degrees, so greater than 48 degrees, not a single one of my light rays is going to go up and be available to be seen by anything on land. They're just going to bounce off, and I'm essentially invisible. So you can actually see some images of things going invisible as they float up in the water column, which is like a little bit absurd. Okay, so I mentioned that there are a whole bunch of really cool applications of this. I'll show them off later when we have an opportunity to do some demos and basically fish through YouTube.